Hello. Um, so I'm Wes Brewer. I'm going to be talking about our work that we've done over the past couple years on developing a digital twin of the Frontier supercomputer, and we've extended this to be a framework for developing a generalized framework for developing digital twins of liquid-cooled supercomputers. This work was done in collaboration with 10 other of my colleagues at ORNL, and their help was instrumental in being able to uh, get this project finished. So I work at ORNL at the Oak Ridge Leadership Computing Facility. We are a Department of Energy Office of Science user facility where scientists from around the world can apply through various programs to get time on our machines. Um, I'll tell you why that we're interested in digital twins a little bit into the talk, but one thing I wanted to say is that we've developed a digital twin framework, and what makes us, and we're not the only ones that have developed such a digital twin. There's been others that have done this. However, our um, work is unique in that it's the first really comprehensive, all open source framework that's been developed for an exascale system and comprehensively studied the workloads running through the digital twins itself. So let's move on to so before I can getting into any details, I want to first define what is a digital twin so that we're all know that we're talking about the same thing, because if you ask 1,000 people what a digital twin is, you may get 1,000 different answers. So I really like this definition. It says that a digital twin is a set of virtual information constructs that one mimics the structure, context, and behavior of an individual or unique physical asset. This is usually done using either AI/ML or modeling and simulation. Two, a digital twin is dynamically updated with data from its physical twin throughout its life cycle, which is typically done using sensor data or what we call telemetry data from the physical HPC system. And three, informs decisions that realize value. And this is really important. The end goal is that we build something that's going to provide some level of value through being able to inform decisions. This definition is from the AIAA Digital Engineering Integration Committee. Was later expanded by the National Academies of Science. So to talk about digital twins, we need to go all the way back to 1970, where in the Apollo 13 mission, actually NASA had developed about 15 different simulators that were able to completely reproduce the conditions on the spacecraft. So what happened in Apollo 13 was shortly after they took off, uh, an oxygen tank exploded, and so the three astronauts spent the rest of their entire time, instead of going to the moon, trying to figure out how they can get back home in one piece. This is where we get the famous phrase, Houston, we've got a problem. So in our work, we haven't saved any lives yet, but um, as you can see, just over the last year to 2 years, digital twins have become extremely popular. So if you haven't been paying attention to digital twins, you might want to start paying attention to them now. And so digital twins have many use cases. When we started our project, we talked with a number of engineers, and we came up with a number of possible use cases, and then we categorized them into 6 different categories, which I show here. In this work, we haven't investigated all these use cases, but we've mainly been focusing on these 3: virtual prototyping, what if scenarios, and insights from visualizations. So in our work, we're developing a digital twin of the Frontier supercomputer. I guess most everybody's heard of Frontier at supercomputing. It was the #1 system on the top 500 until yesterday. Uh, Now it's the #2 system at 1.35 exaflops per second at a sustained 24.6 megawatts. It has a 28 megawatts of peak power and about 38,000 GPUs and 60 million parts. Frontier is a part of a number of history of supercomputing at the Oak Ridge Leadership Computing Facility. And what we see in this graphic here is that uh, significant improvements in energy efficiency were necessary or were instrumental in being able to achieve exascale. So if we were to take Jaguar in 2009 and scale that up to be an exascale system, it would have required 3 gigawatts per exaflop. This was drastically reduced by the introduction of GPUs in Titan down to 330 megawatts per exaflop, and then again down to Summit going from air-cooled to liquid-cooled system down to 65 megawatts per exaflop, and then again down to Frontier, which is about 19 megawatts per exaflop. So what we see with this flattening curve is that there's diminishing returns on energy efficiency with existing approaches. On the topic of operational energy efficiency, there's been a lot of work that's been done recently on studying telemetry data and also on isolated simulations of cooling power or cooling and that. And so one thing that digital twins can do, it can merge both the telemetry and the simulations to provide a holistic virtual representation of the system. And what our main hypothesis for this work was that digital twins can enable or can be a key enabler of end-to-end optimization. So it can be used as a sort of advanced tool to study different strategies for improving energy efficiency. So what we're going to cover in this talk is exploring the development of ExaDigiT, which is a digital twin framework we developed in the process to model Frontier, discover how digital twins can be used to optimize energy efficiency, learn about power cooling and augmented reality modeling techniques, see why telemetry is key for validation, and understand how to reduce energy losses using direct DC power and smart rectifiers. So our development of this framework took about 2 years, although for those that use our framework, it doesn't have to take 2 years to develop a digital twin. We're now developing new digital twins in a matter of a month or two for some of the systems. So let's get into the development details. Digital twins can be composed of simulations, machine learning, and telemetry, and all these work together in a synergistic way to create the digital twin. And so simulations, what we found was that simulations are the primary building blocks of digital twins, and they're very good for virtual prototyping of future systems. We found that machine learning is very useful for modeling workloads. And we found that telemetry is useful for validation and system insights. Our framework has 3 main modules: a cooling module, a visualization module, and a resource allocator, what we call a resource allocator and power simulator. The cooling model has several models within it. It has a thermo-fluids model, a control system model for staging on and off pumps and heat exchangers and that. And the outputs of both of these models are used to compute a power usage effectiveness. The resource allocator and power simulator also has multiple components. It has a workload generator that can either use telemetry, the jobs from the system itself, or generate synthetic jobs. Those jobs can be either replayed if they're telemetry jobs, they can be replayed just as they were played originally scheduled on the system, or they can be rescheduled using a built-in job scheduler. And um, then we have a system power utilization model that's able to predict the total system power and also the aggregated power at the various CDUs, cooling distribution units. Those become the inputs into the cooling model. This is a deployed version of the cooling model on the left. And this gets incremented over time, uh, like once per second, generally, uh, in a forward time simulation. And then we have a visual analytics module, which consists of both a web-based dashboard and for launching what if scenarios, and an augmented reality model for interacting with the system in a 3D way. And now we can also replay telemetry through each of these modules, either for system level insights or to do validation studies. So to understand, to be able to model the Frontier's power system, we have to understand how its specifications. So each rack is supplied with 480 kilowatts of power. This is divided over 32 rectifiers. So you can see here on a cabinet, each cabinet has 4 shelves. Each shelf has 2 chassis. Each chassis has 8 blades. Each blade has 2 nodes. So if we expand this chassis here and we blow this up, this single chassis, you can see the 4 rectifiers providing 380 volts DC, and then each blade here containing 2 nodes. Each node has these two, each node has a SIVOC, a super intermediate voltage converter, which converts the voltage from 380 volts DC down to 48 volts. And the important thing in developing our model is we had to be able to account for things like AC to DC rectification losses and voltage conversion losses. So the way our power consumption model currently works is we represent jobs by CPU and GPU utilization traces. Typically, these are at 15-second intervals, average over 15-second intervals to match the telemetry data we have, but they can be user specified at less than that as well. So every 15 seconds, we compute the current CPU and GPU power and aggregate the power on all the nodes. And then we apply DC to DC voltage conversion losses at a node level. We also apply AC to DC rectification losses at a chassis level. Frontier's cooling system is composed of 3 main cooling loops, a cooling tower loop, a primary pump loop, and 25 of these CDU rack loops. So CDU is the cooling distribution unit, and it provides cooling to 3 racks or 384 nodes. And so these 3 loops are each connected via heat exchangers, up to 5 heat exchangers here. And and you see the individual numbers throughout this schematic. Those are the different locations where our cooling model is able to make predictions of pressures, temperatures, and flow rates. And you can see this goes all the way up to 87 locations, since there's 25 of these CDU rack loops. So are the models able to predict pressure, temperature, and flow rates at 87 different locations? It also is able to predict the staging on and off of the main pumps here, which pump the water at 6,000 gallons per minute, and also the heat exchangers here. The cooling model, we used Modelica to develop our cooling model. This is a small excerpt from the cooling model, the schematic. And why Modelica? Well, we spent a lot of time actually evaluating different commercialized codes, and one thing we found, not only were they very expensive, from on the order of like $50,000 to $100,000 a year to use, They are also, many of them didn't support in a robust way transient cooling dynamics, and they weren't very extensible. So we chose early on that we wanted to focus on open source solutions, developing an open source solution. Modelica provides good transient solutions, and we do because of our work in the nuclear energy. We have a group that's really good at developing thermal fluid dynamics models that we were able to tap into to help us with this. So this plot we wanted to show the sort of the coupling between the power. So if we could provide the purple here is a total system power. So if we provided a synthetic power signal that went from idle 7 megawatts up to what would be representative in HPL run on 9216 nodes, 23 megawatts. We just wanted to see how the cooling system, the cooling model would respond, if it would respond in a transient way. And this was just a verification that the cooling model actually does respond, does handle well in very good way transient dynamics. So ExaDigiT has multiple ways to interface with it. We have an augmented reality model that initially we were using the HoloLens headset, but we're extending this to work with other headsets like Apple Vision Pro. And it also has a console interface that we use sort of at a programmatic level. And it also has a web-based dashboard that the idea was for HPC engineers could use it to launch what-if scenarios. So this is just a 2-minute video that shows all the various functionality of ExaDigiT on Frontier, or Frontier on ExaDigiT. So here, Cedric and Matthias are putting on their HoloLens headsets, and now we're in augmented reality mode. This is the desktop version of Frontier, and he's interacting with the cabinets. Now this is an overlay version of Frontier. He turns on the power on the rectifiers and opening up blades now, and then is able to show power on the GPUs. Now we enter pure virtual reality mode. We can turn on the slingshot network visualization. We can show power on the CDU racks. We can then we can decompose or deconstruct a cabinet, show the power on the rectifiers, open up the individual blades, show the power on the GPUs. Now we show the resource allocator and power simulator, scheduling jobs in a super fast way, and all the power and cooling going on. Now we can open up a cooling distribution unit. We can see the pressures, temperatures, flow rates in that. Now we show the web-based dashboard. These are our top 500 runs from June earlier this year. Now we can show the staging on of pumps, the main pumps, the heat exchangers, the cooling towers. You can see these staging on and off. And then you can see the individual temperatures, pressures, and flow rates in the central energy plant. And now we're going to go in augmented reality mode in the central energy plant, and we can see the pressures, flow rates, and temperatures. So the National Academies of Science, Engineering, Medicine put out a report on recommendations for digital twins earlier this year. And one of their primary recommendations was that verification, validation, and uncertainty quantification, or VVUQ, should be deeply embedded in the design, creation, and deployment of digital twins to establish trust in the virtual representation. And so we took that very seriously, and we spent quite a bit of time actually trying to work on validating our digital twin. And we do this using, we found telemetry was key to be able to do this. So we could replay telemetry through the digital twin and then compare our predictions with the telemetry data. And so this is now for the cooling model. It's showing the temperature, flow rates, pressure, and system PUE, power usage effectiveness. And here the black is the ground truth or the measured data, and the red is our predicted model. And in almost all of our predictions were within 5% error. On the supercomputer side, for the power, we initially did power verification tests to see how well we could predict idle power and peak power. We can do this within 2 to 3% accuracy. And um, then what we did is we said, okay, let's look at a 24-hour day and replay. In this case, was 1,238 jobs in a 24-hour day with a few HPL runs there in the middle. And in this case, the black again is the measured SCADA power. The that's the power is on the right Y2 axis, and the red is our predicted power. So you can see our predictions are pretty accurate, um, usually within 5%, but even sometimes much less than that. The orange here is system utilization in terms of nodes allocated. The blue is the cooling efficiency, and the green is the energy efficiency. So our digital twin can output all this kinds of information. And just in case we got lucky on that one, here's another completely different day with pretty challenging work power dynamics. And you can see our power predictions are pretty decent. So once we had done these validation studies, we said, okay, now let's replay at that time all the data, telemetry data we had on Frontier, which was about 183 days. And we played these all through Frontier, and then we computed statistics in terms of job scheduling information, power, conversion losses due to energy conversion losses, carbon emissions, and all those kind of things. And one of the main things we found is that considerable losses are incurred during both AC to DC rectification and DC to DC voltage conversion. They amount to 1.1 megawatts on average, and with peaks up to 1.8 megawatts. And so if you were to do a peak power breakdown of how the energy is being used on Frontier, the losses account for 6%, which is a significant number considering that it's more than the NIC, RAM, switch, and NVMe. It actually accounts for $1 million a year. So the next thing we did is, can we do some simple what-if studies to see how we can mitigate or improve energy efficiency? And so the first test we tried was what we call smart load sharing rectifiers. And the idea here is that can we put unnecessary rectifiers in a standby mode when like the system when they're at low utilization, and doing this and then making this kind of change to be able to implement smart load sharing rectifiers and then replaying the same 183 days of data, we could now show that it would lead to $120,000 per year savings for Frontier. The second test is, can we provide 380 volts DC direct power? And when we did this, we showed that it increased the system efficiency from 93 to 97%, potential savings of $542,000 per year. This worked well for Frontier, but how about for other systems? I asked this question because this was one of the main criticisms we got for our work, our main feedbacks, I guess. So we spent 4 to 5 months just working on generalizing ExaDigiT so it works for different types of systems easily. And in doing this, we moved to creating JSON input specification files for all the configurable information. So almost everything now is specified by JSON input specification. For the telemetry data, we provide pluggable telemetry data loaders. So you just write a custom data loader for your individual telemetry data. And then we also developed something called Auto CSM, which is a Python tool that actually generates Modelica code. So this is to lower the learning curve of using Modelica to develop cooling models. And so we've been working on developing digital twins of other systems such as Lumi, Photonics, Fugaku, Marconi 100, and Lassen. Some of these, like Marconi 100 and Lassen, have published open telemetry data sets, which are going to be really useful for providing an open digital twin uh, framework for other people to use and perform studies on energy efficiency. We're still having challenges with heterogeneous systems and multi-tenancy or shared node configurations, which we hope to address in the near future. And so you may be thinking, great, this looks great, but how can I get involved? Well, we've been developing since a little over a year ago. We've started been forging a community, a growing community. We have over 100 participants now from supercomputing centers from around the world and also industrial partners like HP and NVIDIA. And we're going to have a BOF on Wednesday at 12:15, and a number of these uh, people will be involved in those discussions. That's in room B315. So in conclusion, we hypothesized that digital twins would provide a robust end-to-end optimization tool for energy efficiency. We demonstrated effective modeling techniques for power cooling and augmented or virtual reality. We demonstrated the importance of verification and validation via telemetry. We revealed significant energy conversion losses in the power system. We proposed means of reducing these costs using direct DC power and smart load sharing rectifiers. And we developed an open source community important for the sustainability of the framework. And lastly, I just want to give acknowledgement to all the different colleagues from ORNL, HPE, Cadre 5, and the ExaDigiT community who have provided a lot of very useful information that we needed to be able to do this work, a lot of good feedback. And there's my email address. If you're interested, you feel free to reach out. And thank you. And I'll take any questions that you have now.